All right, chemistry, let's finish up our lecture on Chapter 4, Section 3. We are moving on to finish up our electron configurations. Last time in class, we recapped our ability to list the total number of electrons needed to fully occupy each main energy level. We stated the Aufbau principle, the Pauli exclusion principle, and Hund's rule. And then we described the electron configurations of atoms using orbital notation. So today we're going to focus on electron configuration notation and noble gas notation. So let's jump forward to where we left off. Here we go. All right, electron configuration notation. Electron configuration notation eliminates the lines and arrows of orbital notation. Instead, the number of electrons, the number of electrons in a sublevel is shown by adding a superscript to the sublevel designation. A superscript, like an exponent. So helium, the helium configuration is represented by 1s2. Now, how do I know that that's a superscript 2, an exponent of 2? Because there are 2 electrons in helium. How do we know that? Flashback to Chapter 3. Helium is number 2 on the periodic table. That's the atomic number. Also the number of protons in the nucleus. We are still assuming that the atom is overall neutral, no net charge. So however many protons are in that atom, that's the number of electrons that are in that atom. So number 2, there are 2 electrons. Now the lowest energy level available is the 1, n is equal to 1. The lowest energy sublevel is the s. So we have 1s2. So again, the superscript indicates that there are 2 electrons in helium's 1s orbital. So let's look at a sample problem here. The number of electrons in boron is... Whoa, skipped one. Skipped the question. Sorry. The electron configuration of boron is 1s2, 2s2, 2p1. How many electrons are represented in an atom? How many electrons are present in an atom of boron? What is the atomic number of boron? And write the orbital notation for boron. Here we go. Now, the number of electrons in a boron atom is equal to the sum of the superscripts in its electron configuration, which we gave you on the previous slide. So we're going to take those exponents, 2 plus 1, that's 5. 5 electrons. Now, right now, the number of protons is equal to the number of electrons in a neutral atom. Okay, we're assuming the neutral atom part right now. So we know that boron has 5 protons, and thus the atomic number is 5. To write the orbital notation, first we draw lines representing the orbitals. All right, so I have my 1s orbital, my 2s orbital, and then I have my 3 separate 2p orbitals. Okay. Last time in class, we saw Robot Lady represent this as 2px, 2py, 2pz. That is also fine, but a little bit unnecessary for the scope of this course. If you write your p sublevel down here, and then you write 3 blank lines, that is good enough. You're showing that you know that the p sublevel has 3 orbitals. Moving on. Next, add arrows showing the electron locations. Now, the first 2 electrons that we fill are going to fill in the n is equal to 1 energy level. And the only orbital we have in that energy level is 1s. So we add an electron of upspin, an electron of downspin, and we move on to n is equal to 2. Okay? N is equal to 2. That's going to take all of the rest of our electrons. Now, the only question is, do we spread them out between the 2s and the 2p orbital? The answer is no. Because the 2p orbital is higher energy than the 2s, we have to completely fill the 2s first. We have to completely fill the 2s before we move on to the 2p. So we'll doubly fill the 2s orbital, right? That means 1 upspin electron and 1 downspin electron. And then we'll move on to the 2p orbitals. Let's apply this to the periodic table. In the first period, okay, that's a row, that's a horizontal row now, n is equal to 1, the first principal quantum number. And the first period elements, elements hydrogen and helium, their electrons occupy the orbital of the first main energy level, right? Because that's as far up in energy as we've gotten. According to the off-bow principle, after the 1s orbital is filled, the next electron occupies the s sublevel in the second main energy level. This is the next step up. Now, that leads us to this idea of the highest occupied energy level, and that's just what it sounds like. Whatever energy level is the highest energy level that is actually occupied, right? Because we have several energy levels that won't have electrons in them. And if they don't have electrons in them, they are not occupied. So the highest occupied energy level is the electron containing, right, it has electrons, main energy level with the highest principal quantum number. Now, anything below that in value, anything below that main energy level, below that principal quantum number, contains what are considered inner shell electrons. These are electrons that are not in the highest occupied energy level. And energy levels are very, very important. How high energy a certain set of orbitals are is very important to satisfying our off-bow principle. And I wish that it was just super in order, an S, a P, a D, and then an F, and then back to an S, a P, a D, and an F. But that's not quite the way it happens. There's a little bit of a trick to it, and we're just going to have to figure that out. A little bit of memorization, but realize the periodic table is going to help us there. There is a rule. It's kind of like a trick rule. It's called the rule of diagonals. And what you do is you write all your S sublevels all in a row, okay, in one row. 1s, 2s, 3s, 4s, 5s, 6s, 7s. And then right above that, you write your p orbitals, right? There is no 1p orbital, so I don't write one of those. I start with the 2p orbital, 2p, 3p, 4p, 5p, 6p, 7p. Jump up, right? There's no 2d or 1d, so I start with the 3, the 3d, 4d, 5d, 6d. And then there's no 1, 2, or 3f, so I start with 4f, 4f, 5f. Now notice that all the 1s are in a column, all the 2s in a column, all the 3s in a column, all the 4s in a column, all the 5s in the column, all the 6s in a column, and all the 7s in a column. So once you've drawn that way, and on a quiz, if you want to draw this, if right when I hand out your quiz and you start your quiz on your answer document in the space provided below, if you want to actually sketch this out, you can do that, right? Because it's coming out of your brain. If you want to write this down to use this rule, this is totally fine. But once you have this little grid constructed, you start zigzagging, okay? Just straight zigzags, This is called the diagonal rule, okay? The diagonal rule. You're always going to fill in this down right diagonal line. So fill 1s first, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s. And then the 3D. And this is the trouble. This is the problem right here. This will help you know that you have to fill the 4S before you fill the 3D. It'll help you know that you fill the, then you go back to the 4P, then you fill the 5S before you fill the 4D. And then when it's time to start filling Fs, that'll let you know that you do 4F right after 6S, right? And then the 5D, then the 6P, until you get the real pattern down. Because it is a pattern, and over time you will get used to it. But this is called the diagonal rule, and I invite you, I plead with you, I beg you to use this rule on a quiz. Moving on to the third period, the outer, after the outer octet is filled in neon, octet just meaning 8, okay, 8 refers to the valence electrons. We haven't covered those yet, but we will. After the outer 8 electrons is filled in neon, okay, the next electron enters the s sublevel in the n is equal to 3 main energy level. Okay, so we're moving on to the n equals 3. We're starting to get lots and lots of electrons here. As we enter n is equal to 3, the third main energy level, we're up to 11 electrons. And so we're having to keep track of a lot of electrons here. And so it's going to transition into the noble gas notation and what it allows us to do. But let's make sure we all remember what a noble gas is. They're the group 18 elements. So that's helium, neon, argon, krypton, xenon, and radon. They're all called noble gases. Noble gas configuration refers to the outer main energy level occupied, okay, the highest outer main energy level occupied. And in most cases, for the noble gas configuration, it's going to be 8 electrons. So keep that in mind. So when we're looking at the orbital notation, because we already have some experience with that, of 3 different noble gases. Okay, if we start at the first main energy level, okay, helium, okay, we fill the 1s orbital upspin, downspin. That's a noble gas, and it's completely filled with its outer, outer main energy level is completely full. When we go to the second principal quantum number, n is equal to 2, the noble gas there is neon. Now, it has all of these 2p and 2s orbitals filled. We can see that. But remember, it still has the 1s full. Okay, that's still full. That's not like it, emptied out. It's still full. These are the inner shell electrons. And so there's this idea that as we fill these electrons stay here. And as we move to the next main energy level, the third main energy level, and we see argon, now we're filling 3s and 3p orbitals. We still have the 2s, we still have the 2p, and we still have the 1s orbitals completely full. So keep that in mind. Those inner shell electrons are always there. They don't go away. They're actually kind of boring in terms of actual reactions, but they are there. They are the inner shell electrons now.
The noble gas notation provides a way to abbreviate electron configuration. In this periodic table, noble gas notation is used to describe the electron configuration of each of the elements. Aluminum has the same basic inner electron configuration as neon. It differs from neon in that it has 2 electrons in its 3s orbital and 1 electron in its 3p orbital. Similarly, oxygen has the same inner electron configuration as helium, to which it adds electrons in the 3s and 3p orbitals. Writing out the entire electron configuration for iodine would take quite a bit of space. Finding the next smaller noble gas and using it as a base makes the notation much simpler. Iodine has the same inner electron configuration as krypton, plus 17 more electrons.
All right, so let's talk about electron configuration. Electron configuration is the arrangement of electrons in an atom. So before we talked about orbital diagrams, and up here we actually have a bunch of orbital diagrams, but instead of having to write all this out to describe where electrons go and how they fit into the atom, we're actually going to make it shorthand, and that way we're going to do electron configuration. So let's start with neon. We know neon has 10 electrons in its neutral state. So when I drew the orbital diagram, this is what I got, with 10 electrons drawn out. Instead of having to draw all of that out, I'm going to do a shorthand version and say, okay, in the 1s orbital, we have 2 electrons, so I'm going to make a superscript of 2. In the 2s orbital, I have 2 electrons, again, a superscript of 2. In the 2p orbital, or sublevel, I have 6 electrons, so I'm going to make a superscript of 6. So this is basically electron configuration. All right, so let's do something a little bit more. Let's do sodium. Sodium has 11 electrons in its neutral state. So, okay, awesome. We're going to say this has 1s, 2, 2s, 2, 2p, 6, 3s, 1. Well, there's something special about neon. Neon we know is a noble gas, meaning all the electrons are filled in the outer shell. So this makes it a special kind of atom or element. So down here, this is 1 more electron than sodium. So instead of having to rewrite this whole thing, notice that this electron configuration is identical to this one. They're the same. So instead of writing this, again, the whole thing, I can just write it, well, sodium has the same electron configuration as neon, plus a 3s1 electron. Easy enough. Okay, let's do chlorine, which has a little bit more electrons. Chlorine, if we were to draw this, if we just simplify this into electron configuration, we'd say, okay, chlorine has a 1s2, 2s2, 2p6, again, same as neon. So instead I'm going to just write neon. 3s2, 3p7. So this is the electron configuration for neon. We're going to call these two, this one and this one, the noble gas configuration. Okay, so which is the same thing as electron configuration, it's just a little bit shorter and easier to write, easier to manage. But what if we come across an element that has 87 electrons, such as francium? That is a ton of electrons, and I don't want to have to draw all this out. This is just a pain. So an easy way to do this is if you look at the periodic table, here's francium right here. The noble gas before francium is radon. Radon has 86 electrons. Francium only has one more. So we're going to say, okay, let's make it easy on ourselves. Let's say it has one more electron. Awesome. So I just have to notify or notice where's the electron coming from and how am I going to denote that? So francium we know is in the 7th period. So we're going to say, okay, great. It's actually, we're going to put 7 there. And everything in group 1 ends in an S1. So we're going to say, okay, great, 7S1. If we were to talk about something, let's say, let's do sulfur. Sulfur, notice it's in the 3rd period. So the noble gas configuration would be neon 3s, and then we go over to the P's 1, 2, 3, 4 P4. So sulfur, if we were to write it, 16 electrons. It would be, what do we say, neon? 3s2. We don't forget, we have to denote that. 3p4. Pretty much easy enough. So that is electron configuration and noble gas configuration.
All right, try to fly through the rest of this. Looking at elements in the 4th period. This period begins by filling the 4s orbital. Okay, that's the available orbital with the lowest energy. With the 4s sublevel filled, the 4p and 3d sublevels are the next available vacant orbitals. The 3d sublevel is lower in energy than the 4p sublevel, therefore the 5 3d orbitals are next to be filled. Again, refer to your diagonal rule. And again, notice as we go from argon to potassium, we're only adding one more electron, so it's actually very easy to represent potassium by simply writing, argon, all of the electrons in argon, plus one 4s electron. In the 18 elements in the 5th period, sublevels fill in a similar manner as in elements in the 4th period. Successive electrons are added first to the 5s orbital, then to the 4d orbital, and finally to the 5p orbitals. Same pattern. So let's run through a sample real quick to finish up. Write both the complete electron configuration notation and the noble gas notation for iron, Fe, and how many electron-containing orbitals are in the atom of iron, and how many of these orbitals are completely filled, and how many unpaired electrons are there in an atom of iron, in which sublevel are the unpaired electrons located. So a lot of questions. The complete electron configuration notation of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and then 4s2. A lot easier to write it in noble gas notation, which is argon, 3d6, 4s2. Iron has 15 orbitals that contain electrons. Okay, 15. They consist of one 1s orbital, one 2s orbital, 3 2p orbitals, one 3s orbital, 3 3p orbitals, 5 3d orbitals, and 1 4s orbital. 11 of these orbitals are filled, and there are 4 unpaired electrons. They are located in the 3d sublevel. And the notation, the orbital notation for 3d6 is represented by the 5 3d orbitals. Only one of them is doubly filled. The other 4 are singly filled. Oh, sorry. Now, write the complete electron configuration notation and noble gas notation for a rubidium atom, and then identify the elements in the second period, second, third, and fourth periods that have the same number of highest energy, energy level electrons as rubidium. So, here you go. Here's your complete electron configuration notation for rubidium and noble gas configuration for rubidium. That means that rubidium has 1 electron in its highest energy level. That's the 5th energy level. The elements with the same outermost configuration are, in the second period, it's lithium. In the third period, it's sodium. In the fourth period, it is potassium. Anything that has an S1 electron. All right, guys. I know that's a lot to take in, but we're really just going over 2 different conventions here, the electron configuration notation and noble gas configuration All right, guys. I will see you next period.